it'll be everyone to, I guess, the first technical webinar that we're having for Earth Observation Australia in 2018. We're fortunate enough to have Professor Arnold Dekker providing the presentation today. Arnold's currently the principal of a company called SatDeck, but before that, I think it was 17 or 18 years at CSIRO before that, dealing with their inland coastal waterways remote sensing group. So again, just a reminder to everyone, if you can keep your mics on mute. If you've got a question, type it in the comments box, raise your hand, or unmute your microphone, and we'll let Arnold get underway. And thanks for your time in talking about this topic, Arnold, and particularly raising something that relates to the Committee on Earth Observation Satellites so that we can engage with it.
Excellent. Thank you, Stuart. So, welcome everybody. A short preamble on why did we do this. It actually started in 2012 or 13 at a European Space Agency meeting for Sentinel-3, Sentinel-2, where it became clear that the European Space Agency was not going to provide any imagery of inland waters for Sentinel-2 because, according to them, there was no demand for it. So they weren't going to atmospherically correct it. They weren't going to provide products for inland water quality at all. And that astonished many of us at that meeting. And the discussion actually started when I was giving my presentation because of questions from the audience. And so there were about 100 people there, experts from all over the world. And I said to them, well, how many of you are going to start using Sentinel-2 for water quality and coral reef and seagrass and shallow water bathymetry applications? And about 2/3 of the people put their hands up. And so the European Space Agency staff there said, you saw them like, oh shit, we may have got this wrong. And I discussed it later with people like Bianca Hirsch and Craig Donlan and others from the European Space Agency. And they said, well, according to us, there was no authoritative document at all on the requirements for inland waters. So we didn't consider them in designing Sentinel-2. So I remembered that. And then when I became involved with CEOS, when I was still at CSIRO, and CEOS had the chair position, we got into the fortunate situation that essentially we could do something about it. So that's what this story is about. So going to the first slide now is that we all know there are terrestrial sensors, ocean and atmosphere sensors, but there have been no sensors specifically designed for inland waters, coasts, estuaries, lagoons, seagrasses, or coral reefs. No satellite Earth observing systems. Yet it is where a large part of the population lives and a lot of GDP is produced. So it's really an odd situation that we faced. Basically, the CEOS actually initiated this through a study, which I'll discuss in a minute. But this is how CEOS and CEOS relate to each other. So CEOS consists of 32 space agencies, and Australia is one of them, and SARA up to now has been the representative. We have 28 associates, amongst others Geoscience Australia and the Bureau of Meteorology. So CEOS concerns itself with the space segment, basically. And then CEOS wants to translate spatial information for the benefit of society, and Earth observation is a massive part. And governments are a member of CEOS, and there's also 126 organizations which are associate members. And so this is a powerful grouping nowadays that really determines a lot of the what's happening in Earth observation. So this is the scope of this feasibility study. It started with the Geo Water Strategy recommendations in 2015, where one of the 10 recommendations to CEOS, one was on the benefits and technological difficulties for a hyperspectral satellite mission focused on inland water quality measurements. We discussed this in Geo Aqua Watch community, which is the inland and near coastal water users community and providers community. And we said, well, we think inland water is actually a narrow scope. Why don't we extend the scope to either an imaging spectrometer or augmenting designs of planned spaceborne sensors to make them be much more useful for inland near coastal waters, benthic and shallow water bathymetry applications. And we discussed that with CEOS, and then the CEOS agency said, yes, but really focus on that augmenting designs of already planned terrestrial and ocean color applications or sensors, as that could be a very cost-effective way. And important, the focus is on a global mapping mission. So not on a one-off experimental mission. It's on a global mapping system. That's why we called it a feasibility study for an aquatic ecosystem, Earth observing system. We had a great team that was put together through CEOS with technical experts, engineers, space engineers, but also application experts and algorithm experts. Really a wonderful cross-section, which made it quite hard to write a comprehensive report because the styles and the approaches of everybody were very, very different. But that was an interesting challenge, doesn't matter. What you can see is we had a really good group from across the world. The table of contents. So we looked at, well, okay, what is the situation around inland waters, coastal waters, benthos and shallow water and bathymetry, which I'll call aquatic ecosystems from now on. And I'm actually excluding oceans. They are a big aquatic ecosystem, but for this discussion, I'm keeping it limited. So we've got a chapter on the Science and Applications Traceability Matrix, together with an appendix, Appendix A. Chapter 3 is much more the engineering aspect. Chapter 4 is about, okay, if you would launch such a system, what would you need to do? And then, of course, the summaries, etc. And the report, the final report, is now available from the CEOS.org website. If you just go to CEOS.org, go to About CEOS and Publications, you'll find it at the top of the list at the moment. So, inland waters are not so simple. Many different land water boundaries. This is just an example of Lake Burley-Griffin at 600 meters altitude in Australia. But inland water bodies are from 408 for the Dead Sea right to 6,400 meters in in the Himalayas. Some lakes that melt one day a year or something. And even in Lake Burley-Griffin, on one day, you can already have quite a variation in watercolor. And we have complex systems such as Lake Eyre. Really, this is after floods. Beautiful colors, but trying to interpret this is, of course, hideously difficult. But nevertheless, they are important environmental ecosystems. We go to coastal waters. This is just a compilation, I think, of the Great Barrier Reef, Gulf of Carpentaria, and Darwin, and the Van Diemen Gulf. An amazing variability of watercolor, ranging from water coming from tropical rivers right through to deep ocean water. Oops, sorry, pressed the wrong button. Okay. Coral reefs. Very complex systems, very heterogeneous. Again, not such a simple environment to deal with. These are images from QuickBird of the Coral Sea Islands, and in this case this is Lihu Reef, which is 700 kilometers offshore on the Queensland Plateau. The water goes down to 700 to 800 meters depth at the front of this reef. The little red blob you see is the vegetation on the coral cay, so it's a false color image. But this is a typical example of where Earth observation could really help manage and monitor these reefs. Seagrasses and intertidal areas, again, very heterogeneous, very different types of vegetation, sparse vegetation, dense vegetation, three-dimensional effects, wave effects, you name it. So we said, okay, we need to know the end user requirements, and the generic end user requirements are quite easy to get to. So, for instance, status, condition, trends, and anomalies. What is where? Which is what a lot of Earth observation at the moment is about. We should go to condition and to trend. sorry, we should go to condition and trend. Is it getting worse or is it improving? The state of the environment reporting, for instance, and anomalies. If we go to Earth observation, what can really be measured directly, in the water column, they are the phytoplankton pigments, including those of cyanobacteria, total suspended matter, color dissolved organic matter, and 3 ways of measuring transparency. And if the bottom is visible, bathymetry and topography. Research and development at the moment is going on into phytoplankton functional types and particle size distributions. When you can see the bottom from the surface or from space, you can look at extent, main species differentiation, if they are spectrally and spatially discriminable, density of cover and biomass. And similar for coral reefs, but also, of course, bleaching. For intertidal rock platforms and beaches and mudflats, similar criteria for what you can measure from remote sensing. But I have to stress there has never been a sensor designed for these environments. If you go to the more broader environmental management issues, you start getting into these kind of key environmental data records or emergency response systems. And I'm not going to, you can read them, I'm not going to go through all of them, but this is actually where, in many ways, the real funding sources would be in being able to report to these kind of requirements. And I think national environmental accounts are becoming really important now. United Nations Sustainable Development Goals are becoming important. But we should also think of, a significant billion-dollar industry now in Australia, like aquaculture. So the generic end-user requirements are known, but the specific requirements that you can translate into a sensor system specifications are very difficult to, that's what we found, are very difficult to find. We did start with the Science and Applications Traceability Matrix in the report, the Appendix A. When you read it, you'll actually find we've got a lot of the matrix is empty because we just couldn't find good, solid, well-founded information on what the end-user requirements would be of an Earth observing system. And this is a chicken and egg situation because we don't have a sufficiently large end-user community that can actually come up with those requirements, meaning the end-user community potentially is large. The one that uses Earth observation is still relatively small. So any help would be appreciated. If people know about publications, reports, brochures, podcasts, any other media sources of true end-user requirements that we can translate back into sensor requirements, that would be fantastic. Because it's something we really realized was much more difficult than we realized when we started out with this project 2.5 years ago. So question to the audience. Sensor specifications. We looked at all these sensor applications requirements. I'm going to focus here on temporal, spatial, and spectral resolution. The others are more engineering type issues that also need a lot of attention, but temporal, spatial, spectral is, of course, are the prime ones without which we can't do effective work. So temporal resolution, this was done by Leo Limburner at Geoscience Australia, which is all the Landsat images of Lake Burley-Griffin. To the right, you see the entrance of the Molonglo River. On the left is the Scrivener Dam. And this is 26 years of Landsat data of total suspended sediment. In the transect, you see black across the lake. And what you see is that till 1998, the lake was very turbid. It went with the millennium drought, it became much clearer. There were also quite a lot of water quality measures taken at the same time, so it's a combined effect. And then you see in the millennium drought quite clear water, less clear towards the Molonglo River on the east side. And then in 2011, you see some major pulses of water, which was when we had some massive floods where a lot of accumulated erosion material flooded into the lake, and the lake was just a creamy mud color. Of course, this is a low temporal resolution, but with a long time series, there's a lot of relevant information there, but not suitable for monitoring. Because what do you do when you want to detect and monitor algal blooms? You'll need a much higher temporal resolution. And these are some blooms across the world. Top left is the Baltic. Bottom right is in Nicaragua, and the middle left, I can't remember anymore. But these are some examples from others from South Africa. So these are examples from all over the world of algal blooms. Of course, one image every 16 days under cloud-free conditions is not enough, as for instance the Landsat frequency is. And this is a lake in Italy. Where we need to go is work like this, which is a prototype early warning alert system done between CSIRO and the New South Wales Department of Primary Industries, looking at Lake Hume. Using, in this case, the Landsat imagery, making it web available and indicating when the color goes red, there's a very high likelihood of an algal bloom in Lake Hume, which will then affect the Murray River if Lake Hume water starts being expelled into the Murray River. So the temporal resolution requirements are actually all over the place, and this is really one of the difficulties in designing a Earth observation system for these aquatic ecosystems. Because you've got hourly requirements, you've got daily requirements, you've got weekly requirements, and you've got seasonal and yearly to decadal requirements. And that makes it really hard to say, well, how many sensors do you need at what temporal resolution? Because we have an extremely variable set of requirements. Spatial resolution. This is an example of some work done in Wallace Lake by CSIRO, the Aquatic Earth Observation Group. On the red square box, we're going to look at some of those islands. Here we're looking through a water column of about 1 to 2 meters, extremely clear water. We're looking at seagrasses and some macroalgae on sand. And you can see the difference between Landsat 30 meters, ALOS 10 meters, QuickBird 2.6 and WorldView 2 imagery at 1.6 meter resolution. Of course, everybody says, we need 1.6 meter resolution. But for a global mapping mission, that means WorldView 2 type data, which costs $15 to $30 per square kilometer. So suddenly for global monitoring, that becomes very expensive. So the question is, can you make do with 2.6 or 10 or 30 meters or something in between? These are supertidal, intertidal and supertidal vegetation, also in Wallace Lake. And again, it's much more attractive to have WorldView 2 data. But could you work with ALOS or Landsat data for a global mapping mission? That's the question. And Mark Matthews in South Africa and Aaron Hester, who is now at the University of California, did some calculations, and they showed that for the world's lakes, that you could use ocean color sensors, especially Sentinel-3, which is ideally suited for water quality, and you would actually cover 44 or even 60% of the total area, freshwater area in the world, except it would be only a fraction of the lakes in the world, and many of them are actually in the Northern Hemisphere. Whereas if you want to go to all the lakes that are important for people, especially in developing countries, but all over the world, you'd like to actually be able to measure 40 or 50 or 80% of all lakes, not the area, but the number of lakes. So you actually really need to go down to the 33 or 15 meter resolution to make it of benefit to all of society. For rivers, a similar calculation was done. And it's actually much more difficult with rivers because of their elongated shape. And you can see that with the current and future ocean color sensors, we can only do 1% of river reaches. But if we go to 33 or 17 meters resolution, it becomes 12 to 24%, and that becomes relevant for management purposes. Spectral resolution. There's a lot of information in the report about spectral resolution. I'll give some examples here. This is the Fitzroy River estuary, where sampling was done from upriver through the estuary into the Coral Sea. And you can see the different colors, where blue is, of course, the coral sea, and then as you go to brown, you start going into the river, and you can see the massive spectral differences. Similarly, you can look at benthic substratum, and people should not forget to measure the sand and the mud as well, because in a remote sensing pixel, they often occur together with the seagrasses and the macroalgae. And here are some of these spectra where you see most variability is between 500 and 700 nanometers. So in the report, there was a massive bioptical modeling exercise done, and it was really interesting how sparse good data sets are, because from all over the world we had to combine data sets to actually be able to do proper bioptical modeling, where we used the WASI system from Peter Dekker at the German Aerospace Laboratories. And he did a lot of work on this for us, running hundreds of thousands of simulations, where we included optically shallow and optically deep water. And so this is a physics-based approach. And then we came up with this kind of graphs which summarize what the spectral resolution is that you need to be able to detect total suspended matter, top left, then chlorophyll, the slope of the color dissolved organic matter, so the spectral slope of the decrease of absorption with increasing wavelength, which varies from inland waters to ocean waters, and then, for instance, estimating depth or bathymetry. And you see the legend is separated into 2.5 nanometer blocks. So if it's, let's say, light blue, you need 5 nanometer resolution. If it's green, you need 7.5 nanometer resolution. If it's orange, you need 10 nanometer resolution, etc. And what this graph shows you is that there are areas where you can make do with a coarser spectral resolution. So you shouldn't look at the finest resolution. You should look at the coarsest resolution that you can still work with. But for instance, for chlorophyll, if you look at that 400 to 450 area, you see that as the concentration increases, you can make do with coarser spectral bands. But that's the kind of information that you need, and it's a clever way of showing, condensing hundreds of thousands of simulations into one graph. There are a lot more of these scenarios in the report for those that want to look at this. So then we summarized this into a table where we said, well, either using imaging spectrometry or multispectral imaging, it would be great to have these spectral bands to detect all these variables in the water column. PFT are phytoplankton functional types, which means do they fix nitrogen? Do they have a certain role in certain environments? Do they produce dimethyl sulfate? Do they, what is their carbon sequestration? So that's what phytoplankton functional types means. And there's quite a lot of, a lot of we found is pigment related. So we often found that if you would want to discriminate pigments, either in seagrasses or macroalgae or corals or within the water column of algae, you need that 5 to 8 nanometer resolution. And if it becomes coarser, you would actually not be able to discriminate some specific algal or coral or seagrass or macroalgae pigments. CPE, cyanophycoerythrin, is a cyanobacterial algal pigment. And if we go on into the red and near-infrared wavelengths, there are also cyanophycocyanine, another cyanobacterial pigment. The chlorophyll bands in the red edge, and then the red edge and the fluorescence line height, baseline. And then towards the near-infrared, it also becomes very useful for detecting suspended sediment separately from the chlorophyll and the color dissolved organic matter. This goes up to 775 nanometers, because that's where effectively you stop doing water quality. But it would be good to have spectral bands for atmospheric correction purposes, sun glint removal, and non-algal particulate matter concentration estimation into the further infrared. So this is the full set of spectral bands that would be ideal to have for such a sensor. This is the summary of the spectral and spatial resolution. Oh, okay, sorry, I have to go back. What we found, which was very different in this study, is that we thought radiometric resolution would be maybe the first or second order priority. And we found actually that for the aquatic ecosystems, spectral resolution is essential because you want to be able to discriminate the different vegetation types, phytoplankton types, corals, seagrasses. Secondly, spatial resolution was essential because when you get mixed pixels, you've lost basically, there's no value to the data anymore, so you don't want mixed pixels. So this was quite novel in this study. We said, well, spectral spatial is very important, and the radiometric resolution should be as high as possible as is technologically and financially feasible. But we didn't put a very strict limitation on radiometric resolution. And a lot of space agencies I've spoken to have said that is fantastic because that's the killer requirement that often makes these sensors extremely expensive. So it's a different way of thinking. And of course, temporal resolution is really important, but that depends on the constellation you use, whether you use polar orbiting or equatorial orbiting, low Earth orbits, or geostationary orbits. And so that's a different question altogether. But what's really important, and I'd like to ask anybody on this webinar to actually give feedback whether the specifications we've given in this report, how useful they would be for all these other applications, because the chances of getting such a sensor will increase if there are more applications that would benefit, not just the aquatic ecosystems I've discussed here. So feedback welcome here. Publications that you know of, that you say, hey, wait a minute, that's very close to the recommendations for other applications. This is really important information because we're having quite a lot of discussions with both startup companies, universities, CRC type organizations, but also big international aerospace companies. And they all want to know, well, what are all the application areas? And is it a solid end user market for this? Going to the market is large because billions of dollars are spent in monitoring these ecosystems. But it's highly fragmented. It's not like there's a one big user who will fund the sensor, no. There are big players, but the World Bank, United Nations organizations, etc., they all would rather focus on the use of the data, and it's unlikely they'll invest in funding such kind of Earth observation systems. National governments, defense and space agencies and aerospace companies are more likely to invest, but they would want to know why. So you have to give them a real answer. So going to my final slide, we've identified a niche area where Australia has a significant amount of expertise and requirements. It's a true Australian space industry opportunity, probably in partnership with national and international partners, and welcome any discussion from anybody. And that's the end of my presentation.
Thanks very much, Arnold. I guess we just open it up to the floor for questions and maybe even responses to Arnold's request for, I guess, input on other applications of that particular set of specifications. I think just, Arnold, just to jump on that, it'd be good to get some responses now, and I see we're starting to get some typed in, but maybe we could send around just a summary table of those specifications to the Earth Observation Australia list and then get feedback systematically that way. I mean, we've got a number of people on the talk, but I think we could reach out to a larger group.
Definitely.
Okay. All right. I don't know if anyone wanted to raise their hand or... so Stefan Myers got a question. So.
Yeah, it's regarding, obviously, spatial resolution is one thing, but what about coverage? So, because a sensor like that potentially produces a lot of data, so you probably limiting the areas that you're capturing to the ones that you are really interested in? Is that envisaged or?
Yes, so those discussions, you're right. If you would map globally with such high spatial resolution and spectral and radiometric resolution, you do run into the issue of trying to get the data down to Earth somewhere. And that is a limiting factor currently. Of course, if you focus on the aquatic ecosystems, we did I think in the report or in an IOCCG report we've been working on as well, we did some calculations, and you really only have to measure about 11% of the Earth's terrestrial surface to capture all aquatic ecosystems. So that would already be, you can make a preconceived map of where the aquatic ecosystems are, and you could, of course, just switch on the sensors there. But then you don't use it for the other terrestrial applications. So, yeah, that's again a compromise you may have to take. It is true that we're getting more and more data relay satellites in space, and if more countries would be involved with their receiving stations, you could, of course, solve the problem that way as well by having many more download opportunities. The problems with NASA and ESA with their massive Earth observation systems, they often only have two receiving stations, and that, of course, makes life then very difficult for data rates. If you had 20 receiving stations, could be possible across the world, and then you would be able to probably download much more. So
I don't think it's such a big issue, because I think there are applications in agriculture, horticulture, but again, these are just some specific areas that you're interested in then.
yes.
I think that there are probably limited applications for a complete global coverage. So I don't think this is a big issue.
No, so we do say that ideally you would probably go for a geostationary set of satellites, polar orbiting, and maybe equatorial orbiting satellites to tackle the tropical cloud issue. That would be pretty expensive though. So somebody would have to fund this. But we also said, well, let's think big rather than think small. Let's just say, well, this is what would really be necessary. And then, of course, we can talk about compromising. It's the same with the spectral band. Are all the spectral bands necessary? No. If somebody said, well, let's say if somebody says for $150 million you could get all your spectral bands, and for $80 million you can only get half of the spectral bands, but then the chance of it being funded is 90%, whereas otherwise the chance of it being funded is 10%. Those are the interesting questions that we may have to go to into the future. But we thought, let's get an authoritative report written so that no space agency can ever say, we didn't know the requirements.
Mm-hmm. Mm-hmm. So, just another question while people are thinking about others. To what extent, Arnold, in the process you went through, did the commercial sector, I think, express an interest in this? I mean, obviously, government space agencies, in terms of the time frames and the scale of operations, is now quite different to some of the companies that we're seeing building and launching satellites. So, I mean, is part of this something that you could see working not on a CubeSat, but at a small to medium type satellite that a commercial company would fund and make money off?
Definitely, and there are conversations going on with such companies. Mm-hmm. So effectively I'm talking to small startup companies right through to large aerospace companies. Mm-hmm. They all say, look, and basically the feedback we're getting, okay, it's a great report, but it doesn't have a market analysis. Mm-hmm. And it's like, yeah, well, that wasn't the idea, to have a market analysis, but we're beginning to realize that that is where the real requirement now is. So what does that market really look like? Which is, again, because of the fragmented nature of the end users, it's very difficult to get a grip on. And maybe this is something that we need, I don't know, universities or government agencies or a space agency or multiple space agencies, maybe even CEOS or GEO, to start looking at, well, how do we find out what that market is?
Yeah, I think that's something that's common across a lot of Earth observation applications now, where people are looking at investing money in this privately, is what's the extent of that market, and how do you go into something and test it and then scale up if it works, and don't if it doesn't. It is a very difficult question because it's a very, very broad set of applications when you start looking at the products and services that can come out of these types of things.
So one solution could be that NMAP, the German spaceborne imaging spectrometer, which will be launched in about a year's time, or less than a year's time, has a lot of the specifications which are called the threshold. So they just fit within the specifications of this report. It will only image, I think, 5,000 kilometers stretching, path kilometers a day. But it could be a good precursor. And the other one is DESIS, DESIS, which is also from the German Aerospace Laboratory, but that's a commercial imaging spectrometer that will be on the International Space Station. It will be launched in July. It will be switched on in September and then provide imagery in January. But the costs for purchasing the imagery are very high. $200 per square kilometer or even more. Right. But we are getting so it seems like we will be having some demonstration type data, which of course could be used to drive the market case for this kind of data. Except if we all keep waiting for that kind of work, it all takes longer and longer and longer. So in the meantime, there are some more agile startup companies that are actually quite interested in this report and the recommendations.
Cool. Thanks, Arnold. All right. Any other questions for Arnold? No.
So there was one question from Fletcher 2. I don't exactly know who that is. About pit lakes for open cut mining. I think that's a great example of where such a sensor would be really useful, because with that spectral resolution, you could actually start doing much more deterministic assessment of what are the oxidizing minerals that are coloring the water yellow, purple, blue, etc., which does happen in these mines. Of course, you need to do some spectral library exploration, but I know in Eastern Germany, in former Eastern Germany, some of that research was done, because when the Iron Curtain fell, a lot of the open pit mines were economically very unsustainable. So they just quit operations and they all flooded and they all turned the most amazing colors. And there was some research done, spectral research done on these mining lakes. So there is some body of work there, and that's a great example of where there's also companies that actually could really fund such sensors. Same with the aquaculture industry. That's an industry that could help fund such sensors. Except, do they want to invest in something which will take several years before it produces data? That's another difficult question to ask to venture capitalists or agencies to fund such a system.
Stuart, it's Tim Malthus here. I had a question, if you can hear me.
Yes, we can hear you, Tim. Go ahead.
Hey, Arnold. Good to hear your dulcet tones again, mate. A question really around, I think much of the discussion you've framed this is around the idea of a new sensor, but I wonder just how much, to what extent also there is the opportunity to actually influence the design of other sensors lined, that are actually lined for launch later on. I'm thinking here particularly of the sort of Sentinel-2 series. Somewhat,
yes.
Landsat's been a bit the same. They've been somewhat sort of closed to the idea of actually modifying the instruments greatly. I mean, Landsat 9 appears not to be that much different from Landsat 8. to what extent can we, can we use something like this to actually influence, say, the design of say, the Sentinel C and D, Sentinel-2 C and D? May not get everything you want, but you might get a vast improvement that allows us to actually do a lot of what the sensor might be designed to do.
So we in the report we went into that more extensively. I just realized that in the presentation I gave today, I skipped that part, that slide, but essentially we said that with the addition of 2 spectral band, well, so one thing we said about Sentinel-2 is because Sentinel-2 has 10, 20 and 60 meter spatial resolution bands. If they would all become 10 meter resolution, it would already become massively more applicable to inland waters, because some of the 20 and 60 meter bands are actually quite good for aquatic ecosystem applications.
Mm.
What we also said is that if you could augment Sentinel-2 with a cyanophycocyanine band centering on 624 nanometers and a chlorophyll absorption maximum at 676, it would already, at 10 meters resolution, it would already enable a significant expansion of Sentinel-2 suitability, both for water quality, but also, for instance, for coral reefs, where they get bleached and then get overgrown by cyanobacteria. And with a 624 nanometer band, you could do some diagnostic analysis if the corals are actually restoring themselves or whether they are being overgrown by cyanobacteria, as an example. And so we have also given those recommendations in the report. And I think maybe we should stress them even more, and probably it might be a good idea to start extracting some peer-reviewed publications out of this report in order to address those questions, because they're in the report, but they might not be clear to all the space agencies.
Yeah. Cool, thanks.
Right, thanks, Tim. Right, some other suggestions in the chat window there, Arnold. So industrial water pollution.
Yes. So definitely interesting, especially if again, if we stay within that 15 to 30 meter resolution, then the water bodies would have to be larger than 3 times 50, so 45, 50 meters at a minimum, in order that you can use this instrument. I think we should also realize that the compromise we took in spatial resolution is that we also realized there are commercial satellites. If you want to go to much finer resolution, you can of course use, for instance, this system we're proposing to detect anomalies, to detect events going on, and then you might be able to target commercial sensors to do very detailed investigations. So that's another way of looking at this, is any system that would come out of this, or any sensor, how would it work in concert with other sensors that are already up there? And indeed, aquaculture, I think, is really an area that we haven't been in discussion with sufficiently, because they are all struggling to meet their environmental impact assessments. And this kind of data could really help them. But of course, it would have to be tailored to their applications. I know that one requirement of aquaculture is also to know which algal blooms are coming from outside of their area, affecting them. They know a lot about potential algal blooms they are creating themselves by eutrophication, but the ones that are really damaging to them in the long term are the ones that come in from the ocean or from coastal currents. And if they could pre-harvest early, when they know there is an algal bloom coming, it can make millions of dollars of difference to even one aquaculture operator. And George Dyke just mentioned that Landsat 10 is a complete redesign, and so I think this report has gone to the Landsat 10 team, and I've done an interview with the Landsat 10 team as well. And so I think this could really have, this report, because it's a CEOS report and now been approved by CEOS, it could really have an effect on Landsat. My view is that Landsat could easily become imaging spectrometer, and you could then counter the argument by a lot of people, but then we lose our multispectral bands. Is, well, if you have an imaging spectrometer with 5 to 8 nanometer spectral bands, you can recreate any Landsat band you like, from Landsat 1 to Landsat 9. So why not make it an imaging spectrometer? But there are there's a lot of conservative views about Landsat. It's a very odd situation, and just recently I saw a paper which was distributed through GeoAquaWatch in Nature that a group is saying that USGS should look at asking money for Landsat data again, which would be a terrible situation to happen. But this is the era we live in at the moment.
Well, thanks, Arnold. That's a good point, which I know a lot of people on this call have been responding to that issue actually over the last week. So, all right. Any other questions for Arnold?
And do feel free to send me emails or phone me or whatever and have a chat, because it is a really interesting area, and getting those end users, not just the description of the end users, but what do they require in reality within normal ranges? What do they require? Because I once asked the National Estuary Network in Australia, what do you want? And they said, well, 1 centimeter resolution twice a day. And I said, okay, are you prepared to spend $10 billion on it? They said, okay, no. So I said, what would be a minimum requirement that would really help you already in work you do? And they said, well, if we could have one good image in every season of our water bodies, our estuaries and lagoons and those kind of areas, if we had one good seasonal coverage per season, so just 4 coverages per year, at about 10 to 30 meter resolution, that would already be a massive improvement over what we do now. And I thought, okay, now that is a good requirement. That's one that is manageable. But you actually need to engage in discussions with these groups of end users before you can get at those kind of answers.
Yeah, that's a good point, Arnold. And I think most of you know that the working groups are underway for our 10-year plan. The 4th working group is focusing on industry and market interactions and requirements. So a lot of what Arnold's just talked about is quite important in that context, and the market-driven side of it's important. Arnold, you got an offer there as well from Ben Koshnik.
Yeah. So, well, we should talk, of course. Mm-hmm. Very good.
Okay. If there aren't any further questions, Arnold, again, I'd like to really thank you for your time in preparing that. I think it's been really useful because the questions you've asked apply across a range of new systems which are being developed, but also across needs across a range of new sectors. So I'm hoping this is going to be the first of several similar webinars that we have, and also that we hear back about how this has progressed as well.